Kevin, go ahead and hold that question. Let's get Zach's done and we'll deal with this. Okay, so basically what I'm saying is show me an isothermal atmosphere. Everybody right now. What does the word thermal mean?
Constant temperature.
It's a constant temperature. So what does that look like? It should look like a line that's straight up and down, right? So this is isothermal. And how would you label that using, that's a question, notation? How did we label that?
I know it's the change in temperature over the change in height, but I'm just trying to find the.
So dTdz, right?
Yeah, dTtz.
And what's true on a line that goes straight up and down?
It equals 0.
Okay, so on an isotherm, there is no temperature change. So from your perspective, show me getting colder with height, everybody. What would getting colder with height look like? Okay, I'm seeing Tom, Zach, you have that. Okay, so that would be a negative dTdz, but a lapse rate is a negative, so that's a positive lapse rate. So what you're showing me this way is a positive lapse rate. And I'm always a little afraid to do this because I'm not sure how you perceive this. So that's why I want you to do this. So once again, show me a positive lapse rate. Okay. Now, you guys are in different. Everybody point to your left. Okay, so your line needs to go to your left. Julia, you and Ryan were backwards then on a positive lapse rate. Remember, a lapse rate is a rate of getting colder, and as you go higher, you're getting colder. So your line should go this way, right? Now, the more that it's this way, like the line's going from here to here, remember we have those drawings. This was on lab 1. What is that lapse rate telling me? So watch this. This is a lapse rate. This is another lapse rate. What is the second lapse rate doing?
It's getting cooler faster.
It's getting cooler faster, which is a great way of describing that. It's a greater lapse rate, right? It's getting cooler at a faster rate, or at least, and we don't want to necessarily think speed, but I would say the same thing, Ryan. It's getting cooler faster. So as you go up, it's getting colder faster. What would this line do?
It would be warmer.
That's getting warmer. And what do we call it when it gets warmer?
Negative lapse rate.
Well, you could say a negative lapse rate, and there's a name for a negative lapse rate. A temperature inversion. So there's a temperature inversion going on. Okay, so stratosphere, thermosphere are inversion layers. Troposphere, mesosphere are positive lapse rate. It's getting colder the higher up you go. So what's important is you got to know that this is the greater speed. The greater lapse rate is more flat. So I don't want you to use slope or steepness because it's an inverse function, because I flipped the independent and dependent variable. That's why we don't answer it like that. So the flatter the line, the greater the lapse rate. The more up and down, the smaller the lapse rate, because straight up and down is a 0 lapse rate. It's isothermal. Does that make sense, Zach?
Yes, that does make sense. Thank you.
This actually is going to lead us into this next discussion that we are going to have. And my internet connection is not really good today. And I know you have a test coming up. So I do have an online lecture that I've given for another class, but it's appropriate for this class. So you're going to be required to watch that before the next class. You could do it today, that would be fine, but I don't want you to get confused, but it's super important. I'll give you the link. I'll send it to you in the chat box. And that will just be a lecture that you take notes on, just like everything else. But this time it's not interactive and you can do that on your own, okay? Now, Aaron's question.
Her question was about the essays on the exam. Is it okay to include diagrams?
It is not okay to include diagrams. You must include diagrams, okay? That is the only way that some of those can be answered correctly. I mean, you need text, but including diagrams would be super important. Not necessarily for everyone, but you definitely want to use diagrams.
Gee, good, okay.
So that will be important. Anything else specific about the test? So Zach, that stuff on lapse rates is super important. And we're going to be getting into that section right now. And then we'll deal with the water vapor coming up soon.
Oh.
So anything else concerning the test? The test is available. The objective portion is available today, later this afternoon, I think. And then it will be available through Sunday night. So you'll have to complete it then. Okay, anything on the logistics of the test? Anything else that we need to talk about?
I was just wondering with Blackboard, I was looking for the Zoom recording so I could go back and like if I needed to, but I don't know, like I tried to look for it and I couldn't find it.
Okay, hold on,
Blackboard, so
everybody.
I was wondering.
Everybody go to this website, because go to it now, because we're going to talk about it anyway. climate.cod.edu/classes. climate.cod.edu/classes. Is everybody on that site?
Not yet.
Somebody give me a negative if you aren't.
Wait, what's the URL again?
climate.cod.edu/classes. So I just got to make sure everybody's there. How you doing, Aaron, Kevin? You guys good?
We're typing it in.
Okay. You should see.
Yeah, we got it.
Okay, you should see this. So click on 1110 for now. And here's all the lectures. And what I've been trying to do this semester is I don't just give you the date. I give you also the basic topic. I mean, there's more to it. It's a long class, but that's basically what we talked about. Okay. So these are your lectures. Everybody got that?
Yeah.
Zach, you good? Okay.
Yeah,
Now,
thank you so much.
parent directory, go back here and go to where it says 1119. Okay, so you're going to 1119, click on Cervatka Lectures. And you are going to watch this lecture. It's called Moisture in the Atmosphere, Lecture 7. So this is for another class, but it's, in all of my classes, there are some things that are just required across the board. Everyone's got to learn moisture in the atmosphere, no matter what introductory class they have. So this is, you'll see.
Hello, everybody.
This is
our
me.
last lecture for Unit 1.
It said, don't worry about like details. If I say it's just the information. So please take notes on that. Really careful. There's a lot of, I've got some diagrams. I've got some examples of things that are going on. Okay. So again, definitions of mixing ratio and relative humidity. These are all things going to be super important. Okay. So that is your assignment. And I will give you time off at the end of class. We will not go, we will cut by 2:30, okay? Is everybody good with that?
Yeah.
Okay. So make sure you've got that. Hi, Shannon.
Sorry, I was late. I had to shovel.
So
Then-
you're gonna be doing the moisture in the atmosphere stuff.
Okay.
By the way, I don't know if you guys seen, if we get another, 15 inches of snow this winter, we'll be like top 5 of all time.
Yeah, it is snowing here again.
And you're getting a little bit of snow. We're supposed to get another probably 3 to 5 inches on Sunday. So it will, after it snows today, it'll just be light, not accumulating snow really. But then we could get another 3 to 5. And then by that point, we could be up over 50 inches on the year officially at O'Hare. I know Midway's got more because of the last snowfall. Do you know they got, we talked about it, they had 17 inches of snow?
Mhm.
Mostly from the lake. They were getting 3 inches an hour. Incredible stuff. In any event, we're starting to hit record territories. We are already one of the coldest Februarys of all time. DuPage County Airport hit a record the other night of 5 below zero. Tomorrow night we could drop down to sub-zero as well. And it's kind of getting late. Why do I say it's getting late to get sub-zero? What's been changing?
The angle of the sun.
The angle that the sun's coming in. It's basically something we call insolation, not insolation, but insolation, which is how much radiation we're receiving. This will be a third unit thing, so I'm not going to have you define it and worry about it now. But we're heating, if you notice, the sun's a lot more intense. This is the time of year that when you drive in your car on a sunny day, do you remember what sunny days look like?
Yeah.
Yeah, it's like super cold outside, and then it's so hot in your car because the sun is getting more and more intense. So that sunlight coming in can really make a big difference. So pay attention to that the next couple of days, and within a week will be officially, what is March 1st officially?
Meteorological spring.
It's the start of meteorological spring. Astronomical spring is not till the 23rd of March, but we're not an astronomy class, we're a meteorology class. So our first spring month is officially March. And we've got some warming to do. We're gonna have a lot of snow to melt. Anyway, so any questions on the moisture in the atmosphere? Please do that as soon as you can. But if you want to take your test first and then do that, I'm fine, as long as you do it before Tuesday. But listen to me, you need to come to class knowing this stuff. You cannot not do this lecture. Okay, this is an absolute requirement. Take notes on it just like anything else, because you better understand this. And it's going to be interesting for me to figure out how much do you understand from a single lecture without interaction. All right, are we good with that? All right, so let's go on to this section that I can do without knowing the moisture in the atmosphere stuff. And this is more discussion, what is instability? How would you define what unstable is, right? Unstable, the adjective, instability, the noun. How would you define that?
Wait, can you repeat what you just said?
Okay, so unstable is the adjective, instability is the noun. So just that's how you use the language. But what does it mean to be unstable?
Rising freely.
Okay, you could say what rises freely?
Air.
Okay, now in this class, how are we going to define what the air is?
Would it be buoyant?
Well, what is buoyant?
Parcel.
The parcel, right? So everything is in respect to that parcel. So here's the technical definition. Actually, why don't you go, what page is this in? What page is this on in your book? On definition of instability. So take a look at your book and tell me what it is. What page are you looking at? Has anybody? Aaron, is your book online? Or do you have a paper book?
We've got the paper text. We're trying to find it. It's not in the index.
Oh, okay. Well, here, I tell you what. let's do this. Let me define something. Let's try this first. And I'll do instability, marble. And I think when I do that, this is because a lot of times they'll talk about instability this way. So the first one, and this is, I don't know what this meta stable is, but they'll do something along these lines. So taking a look at this picture. Stable, and write this down, is when you displace something and it returns to its original position. So here's a marble. If I move the marble left or right, what is the marble going to do when I let go of it?
Roll back.
It's going to roll back. Tim was saying this is page 107. Do they have the marble in there, Tim?
Mhm.
Yeah, they do.
Okay, so page 107 in your book. Thank you. Unstable is if you move the marble, it's going to roll away from its original position. Now, this thing says metastable, and that must be, I don't even know who the hell said that. That must be some physics term. In meteorology, that's called neutral. It's just going to stay there. We're not going to care. Okay. Neutral means you move it, it stays there. So imagine that you had a child that you sent away to summer camp. You send them to Wisconsin for the camp, and then they end up going to California. That is an unstable child. A stable child is you move them to Wisconsin, a week later they come home. That's a stable child. A neutral child is one you move to Wisconsin and he stays there until you move him someplace else. Okay, we are not going to ever really mention neutrality within meteorology, but the idea is this. The stability is based on the parcel that goes up. Okay, so when I lift the parcel, if I let go of it, if it comes back down, that would be considered stable. Okay, now, what if I took a beach ball and pushed it down into the water and I let go of it? What would the beach ball do? It would go back up. Is that stable or unstable?
Unstable, right?
No, because remember, the original position was up here at the surface of the water.
Oh,
I pushed it down and it comes back. So really, technically, the beach ball is stable, even though it is buoyant in the water. So be careful of things like that. Now, if I put a rock in the water, what would that rock do?
Just
Think-
saying.
It would accelerate downward. It would actually get faster and faster the further it fell. It gets resistance of water, but a big rock accelerates because gravity is pulling it down. Okay, so I think we talked about this last Tuesday. We said, all right, I lift the parcel, I let go of it, and now it continues to rise by itself. Why is that? Tom, you were kind of mentioning it. So why is that if I were to let this box go and it continues to rise by itself?
It's less dense than the air surrounding it.
And what
Same
makes
level.
it less dense than the air around it?
Lesser concentration of molecules.
Well, that's what less dense is. Why is it less dense? Right. By the way, Tom brings up a really interesting point when you're discussing science, and listen, I know students who are science students their entire lives, and they have to learn to talk with correct language. And the language that you use helps define your understanding. So he said, I said, why is it less dense? And he goes, well, there's less molecules in a given volume. Do you understand? He's describing what less dense means, not why it's less dense. So be careful of anytime you do that. Why is it less dense? What would make this box less dense than surrounding air?
There's thermal expansion inside the box.
No. What influences density?
mass and volume.
No, that's what density is. What
Sure,
influences
temperature.
density? Tom?
Pressure and temperature.
Pressure and temperature, right? That's the ideal gas law. Pressure equals P equals rho RT. Pressure equals density times R times T. That's the ideal gas law. So if I change temperature or I change pressure, that could affect the density. Now, in the parcel, which one is it?
Pressure.
Do you agree with that? Let's have a discussion on this. Everybody unmute their mic, because you need to understand this. By the way, this is kind of what Unit 1 is. We're still sort of there. So how would you answer? Tom, say what you said again. How would you respond to Tom?
I just said pressure.
Give me a
Is
complete
what?
sentence to discuss.
The parcel is less dense because I don't know. Like,
Zach, how about you try it?
Well, like the pressure is like the same from inside the box as outside the box in that parcel theory, correct? And so, would that make our pressure the constants because it's
Tom, what did you think with what Zach said?
well, I agree that pressure is constant. So I think that for pressure to remain constant, the parcel needs to expand. And when it expands, it becomes less dense and then therefore becomes buoyant.
See, what's happening here, guys, and this is where the confusion is. And I've told you about the 3 levels of learning, right? I speak, you go, yes, I understand, right? That's level 1. Level 2 is when I speak, you understand, and you're like, oh, I think I really get it. Like, I get it, it's the light bulb moment. But level 3 is when you're able to discuss it. And most students, in terms of parcel theory, don't get to level 3 because they don't try to get to level 3. And the reason for the problem is we have 3 spatial dimensions and 1 temporal dimension. 3 space, 1 time. So in order to express a thought correctly, do you understand that grammar is an important statement? An important concept. I know you probably don't, but there is something called present imperfect tense. Do you know what that tense is? Anybody? Shannon, you kind of nodded. Do you know what present imperfect tense? Give me an example about the parcel.
Wouldn't it be like the present perfect tense, isn't it? Like what it is at a certain time.
What's the form of speech that you have to have that you would recognize? Anybody? It's so funny. You guys have all taken English, right? Do you learn stuff in English in high school or college?
Not this garbage.
yeah.
Okay, so then the answer is the parcel is rising. It is occurring. And the reason that becomes important is because as the parcel rises, as it is rising, what is the parcel doing in terms of our 3 important variables of state, we call them? Pressure, density, temperature.
There's got to be an offset in one of them.
Well, what happens to pressure when the parcel is rising?
Decreases.
The pressure, you see, the pressure is decreasing because it's expanding because of the weight of the air above you, right? It's always equal to the pressure outside. So do you understand that in the vertical sense, pressure is decreasing with height? dP/dz is less than 0.
Mhm.
But when I'm talking about a parcel's buoyancy, the parcel is being compared to the air horizontally, second spatial dimension. And therefore the pressure is constant, meaning it's the same as inside and outside. So what is the density doing of the parcel while the parcel is rising? What's the density doing?
Decreasing.
It is decreasing. What is the temperature doing of the parcel as I lift it?
Decreasing.
It is also decreasing. Okay, so pressure is going down, density is going down, temperature is going down. In our teeter-totter, what is everyone doing? In our analogy of the teeter-totter, what is everyone doing?
Just getting off the teeter-totter, just leaving.
No, they're throwing up Twinkies, remember?
Oh yeah.
Yeah.
They're all vomiting Twinkies. All
Idea.
3 of them are. But as the box is going up, what is happening to the air outside of the parcel? Now we go outside the parcel. What is the air pressure doing of the air outside the parcel? In other words, as you climb a ladder in the environment, because you're not lifting anything, so now it's present tense, the pressure is what as I go higher?
Decreasing.
It decreases as well. What is the density doing?
Decreasing.
It is decreasing. Do you agree that the further up in the atmosphere, the less dense the air is? Almost always, not always, always. Sam, we talked about this in the molecular boundary layer. That's not true, but for everything else it is. What is the temperature outside of the parcel doing?
Decreasing.
Tom says decreasing. Do you agree with that?
Regular.
Would it like depend depending on where the height is?
Well,
'Cause-
doesn't it depend on what the atmosphere is actually doing? The temperature in the atmosphere can, listen to this, it's a smart ass answer. If I ask you, what is the temperature of the environment doing? The answer is whatever it wants to do. Could the temperature go up in the environment as you go higher? Yes. That's called an inversion. Could the temperature go down? Yes. That's a positive lapse rate. Could the temperature be the same? Yes. That's isothermal. So the parcel, we know what the parcel does. Why? Because it obeys the laws of thermodynamics. The environment does whatever it wants, which is why we measure it. And what do we measure the temperature of the environment with?
Average kinetic energy.
No, what do we measure it with? How do we know what the temperature in the environment's doing? This is an easy question. Aaron, what do you say?
Thermometer.
He's saying thermometer.
How about a thermometer? Now, I have to go real high. Can I just jump up with that thermometer? What's a better way to do that?
Using a radio
balloon.
Sunday?
Using a what?
A radio Sunday?
Oh, yeah, you don't have to call it, it's not Spanish, but it's called a radio sonde or a radio sonde, I think. I don't know if the book uses. Radio sonde is the way I've always used it. They now go radio wind sonde, so they call it a ray wind sonde. But yeah, you put up a weather balloon and it measures the temperature. So you got to know that information. If we're going to deal with anything, you need to know what the temperature of the atmosphere is doing in reality, because the box only undergoes an adiabatic change. The environment changes because there's different sources of heat. You can change the temperature by radiation, conduction, convection, or advection if we go horizontally. So that's what's going on to the air outside of it. So when I lift the box is expanding, it is cooling, it is going under lower pressure. When I stop and let go of the box, I now compare the box to the outside of the box. The pressure in and out of the box is now considered a constant because it's the same. Therefore, the only thing that can affect density is temperature. How does the temperature of the box compare to the outside temperature? So it's the temperature difference in and out of the box that tells me the density difference in and out of the box. Write that sentence down.
Can you repeat that sentence, please?
Sure. It's the temperature difference in and out of the box that determines the density difference in and out of the box.
We see temperature gradient.
I don't know because, and that's it's an interesting question, Sam. I wouldn't use the term gradient because what's a gradient? Test question.
Oh, change over distance.
It's a change in something over a distance, and I don't need to know the distance from the parcel to the outside. I'm not really dealing with that. I'm just saying there is a difference in the temperature. So I don't care how far the distance is. I'm making this up, right? It's an analog. It's hypothetical. The greater the difference in temperature, the greater the difference in density. Because what's the relationship of temperature and density?
Inverse.
If
pressure is constant.
Which it is. Not because the box is moving up, present and perfect, but because the box is being compared, present tense, to the air surrounding it. You see, when you use language correctly, it actually has meaning. And that's something that most people don't think about until they get older, which is a shame because I would focus on that as a basics. So if it is warmer in the box, then it is less dense than the surrounding air outside. And if it rises by itself, now we say it's what?
Buoyant.
We say the parcel is buoyant because it is rising by itself. The parcel is now considered to be unstable. Question: where did the parcel come from? Where did the parcel come from? Isaac, what do you say to that question?
Isn't the air parcel imaginary?
Yes. Where did I make it? Where did it come from?
With your mind?
Well, no. Like, where did it start? Where did
It started up here, didn't it?
No, it
No.
started down here. And then I lifted it up, right? So when I start it here, what I'm saying is wherever I start it from, what's the temperature and the pressure and the density of the parcel? How would you answer that question, Isaac? Am I breaking up or did you hear that okay?
Well, if it's down here and no, I think I heard it okay. So if it's down here, then the pressure and the density is going to be higher. And if it's up here, the pressure and density is going to be lower.
You're not wrong, but that's not what I'm looking for.
Okay.
What's the temperature and pressure and density of the box of air when I start it? Aaron, are you raised?
Yeah, it's the same as the air around it.
right? It's going to be the same. It's starting at the same temperature, the same density, the same temperature. Then I lift the box up. What is the temperature going to be of the box? Abby, how would you answer that question? What's the temperature of the box as I lift it up?
Doesn't the temperature of the box
Say, I'm sorry, you said, won't the temperature of the box, what?
I'm thinking, one
Oh.
second.
Okay.
So,
Would,
you said
would it,
back to
would it-
what we, I'm sorry, I just want to get this down. So the temperature difference in and out of the box is the same as the density difference?
Well, if it's warmer in the box, it's less dense in the box. The greater the difference in temperature, the greater the difference in density. Go ahead, Abby.
so would it be warmer in the box?
Listen to me when I say this following thing. Again, we're going, I know it sounds weird that I'm talking in English, talking about English grammar. You said it's warmer in the box than what?
The outside?
Okay, I'm not asking for that.
Yeah, okay.
I'm asking what happened to the temperature of the box as the box was rising.
Got warmer?
Does it get warmer? Why does it get warmer? Aaron, what does it get?
He says it decreases, it gets colder.
It gets colder. By what rate is it going to get colder? You should know this because this is on the test coming up.
The lapse rate.
Which one? And anybody can jump in. Which lapse rate?
Would it be the -10 degrees
Which is
Celsius?
called, yes, it would be the 10 degrees Celsius per kilometer, which is called what?
Adiabatic lapse rate.
Okay, say the word adiabatic.
Adiabatic.
It would be the dry adiabatic lapse rate. That parcel is getting cold at the dry adiabatic lapse rate. Now, Shannon, I changed something. I asked you what the lapse rate is, and you said, is it the -10? If it's a negative lapse rate, what is it getting?
Oh, warmer.
Right, so
Positive.
it's a positive 10, right? Because a lapse rate, we're defining it to be getting colder. All right, Tim, here's one for you. If I lift the box and the box is cooling at 10 degrees Celsius per kilometer, and I want the box to be unstable, what is the lapse rate of the air around it?
It's got to be. It's the, okay, so.
See, this is
No,
what I'm trying to see if you can figure this out just by talking.
I can do this. We talked about this a couple weeks ago. So for it to be unstable and to keep rising, it has to be cooler than the air around it, right? The box.
If the box were cooler than the air around it, then the box would be more dense and come down.
Okay, so opposite of what I said. So that means it has to be a higher lapse rate than the box, the air around it.
Isaac, do you agree or disagree?
I'm sorry, can we repeat this?
Yeah, I can repeat it. So for it to be unstable and to keep rising, that means that the box is warmer than the air around it to make it less dense. And
Yeah,
for that to happen, for it to be warmer, the lapse rate of the air around it has to be higher, like a higher lapse rate. It has to be getting colder over the same distance for the lapse rate of the box to be higher or lower, I mean.
Try it again. You're getting closer to level 3. That
Sure.
wasn't bad, but you can see how do you guys see how difficult it is to get to that level? Nobody does it right the first time. But I'm telling you, if you guys ever got there, you'd be amazed at how much better you would do in all of your classes. Because you're actually learning something. So try it again, Tim.
So we're talking about the air around the box and in the box itself here. And for the box to be unstable and to keep rising, the temperature of the box needs to be warmer than the air outside. That leads to a lower density. So when we move into lapse rates, we're talking about the air having to be colder than the box. So it has to have a higher lapse rate over the same distance. Does that make more sense?
Am I answering this?
Yes, you would answer that because it
Anyway,
makes you did
Yeah,
a
yeah.
better job.
I kind of condensed it a little bit.
Yeah. Well, notice, by the way, just point of view, notice how much more fluently he was speaking. He didn't have as many he was able to speak in full sentences. His brain was processing the data and actually expounding on it. Now, Isaac, it's okay if you didn't understand that. So tell me what you get.
I have a really hard time remembering what people say, but so I'm really sorry. I'm lost right now.
So
Why don't you try it, Isaac?
Well, I've forgotten what we're talking about. I understand what he was saying when he was saying it, but I don't remember what we're talking about.
Go ahead, Tim, respond.
So like we're talking about, a parcel or a box being unstable, which means it's going to keep rising. It's not going to stay at its spot when you move it or change it. So the way I imagine this, when we're talking about the air around it and lapse rates, I always do like the lines and everything. Like we start with an isothermal line, I guess, which is at 0. And for a box to be unstable and to keep rising, it has to have a warmer temperature than the air around it. And so that means that the air around it is cooler than the box, meaning that as it moves up, the air is getting colder at the same distance, more cold than at the same distance. So that means the line is further than the line of the box. That's the way I visualize it to help me understand it.
Oh, okay. So what he just said, I'm visualizing it. Isaac, are you having problems visualizing it?
No, I just really have a hard time retaining what people are telling me. It's easier for me to look at it on.
Everybody right now on a scale of 1 to 5, what's your understanding of this question that we're asking and Tim's answering? Where are you on that level? So give me your fingers. Zach, you're flipping between a 3 and a 4. Sam, you're a 3. Julia, you're about a 2. Isaac, you're about 3. Shannon, you're about 4. Tom, 1 or 2. Aaron, you're at a 3. Ryan, where are you at? 3. Okay. So now, Abby, I think that's a 3 or a 4. Okay. So let me just say something for a second. Okay. So the parcel's getting cold, but I want it to be warmer than the air around it. Therefore, the environment needs to get cold faster. Does that help?
Yeah.
The parcel is getting cold with height. So if the parcel is going to end up colder, the environment has to get colder faster.
It's a race.
So, right? So that's what I'm going to say in a second, Sam. Isaac, did that help a little bit?
Yes. So right now we're just talking about everything that we've kind of been discussing for this whole class period, right?
Yes.
Yeah, okay.
So write this down. Instability is a race to get cold between the environment and the parcel. Instability is a race to get cold between the environment and the parcel. That we want the parcel, I'm sorry, that we want the environment to win.
So if I could refer this to the, because with the beach ball, wouldn't the water of the, like the pool or whatever be colder than the beach ball itself? So when you push the beach ball
Well,
into the water.
the beach ball is always going to be less dense because it's not a temperature thing. Air, in a given volume, air has a lot less molecules than liquid.
Okay.
So liquid's always more dense than air. So this is, a beach ball has no purpose in temperature. But if I imagined a hot air balloon, yeah, now we're talking.
Okay.
So if the environment wins, that means it's stable, right?
No, if instability is when that happens. So if the environment wins, we say the parcel is unstable.
Okay.
Now, does that help you on that 1 to 5 level? Does that make more sense? Does that help a little bit? I think a lot of you need visuals. So let's go here. I want to draw on here, insert a, I can't wait to get my pen back. I am so bummed about this. Right. Oh, you know what? I couldn't use this because I don't have my pen. That's what it does. So I need paint. So what I need is this. The parcel, whoa, the parcel is getting cold. This is where the parcel starts. Do you agree?
Mhm.
The environment, and now the environment will, I'm going to use the same color because is there. So here I'm going to say environment, E, and here is the parcel. Do you agree that the parcel and the environment start at the same temperature? And as I lift that box to here, okay, so now I'm going to be back at my little square here. So the parcel will become here. Do you agree that it is warmer than the air surrounding it in the environment? Therefore, it's going to be less dense because because density and temperature are inversely proportional if the pressure is the same. And therefore, this parcel is buoyant. But do you agree that this parcel, look, my arm, is cooling at 10 degrees Celsius per kilometer? So the environment is more this way, which we said is a greater lapse rate. So what that ends up doing for me is the environmental lapse rate has got to be greater than the parcel's lapse rate. But what is the parcel's lapse rate? It's dry adiabatic, which is how much?
10 per kilometer.
10 degrees Celsius per kilometer. This scenario is saying that the environment needs to cool by more than 10 degrees Celsius per kilometer. That hardly ever happens. This hardly ever happens, which means the atmosphere is never, almost never unstable. In reality, what is the average tropospheric lapse rate?
Like,
0.5.
yes.
6.5 degrees Celsius per kilometer. So the atmosphere, if it cooled on this line, and let's go with that line, do you agree that the parcel will end up colder than the air around it? Therefore, if I let go of the parcel, what would it do? It would sink, be more dense, and that's stable because I lifted it, let go, and it comes back down stable. How would you describe this environment lapse rate? This environment's lapse rate, I'm on the brush. This environmental lapse rate is now greater, or I'm sorry, less than. It's so hard to draw without a pen. You guys, you tried to do this, haven't you? You'll see on this little video, I didn't have my pen when I made the video, so I type, which is fine, but my diagram X's are hard to make, so. That's stable air. So the troposphere, generally speaking, is stable. But see, here's the problem. If the atmosphere is mostly stable, how is it that we get thunderstorms? Would you agree that thunderstorms come about when the atmosphere is unstable? I think that should make sense to you. You probably have heard that term on the Weather Channel or whatever you watch. Unstable air is thunderstorms. So if instability is a race to get cold between the parcel and the environment, that we want the environment to win, but the environment hardly ever runs faster than the parcel, what do we need to do? Let's imagine you're running a race. You want to win the race. You're the environment, but you can't run faster than the guy you're running against. They run faster than you almost always. What would you do to them? Do you think you could run faster? No, I can only run so fast. What could you do to them? Couldn't you trip them or like break their knee or something? Because if you could slow them down, then you might win that race. So the key to getting thunderstorms is to slow the rate of the parcel. Well, how do you slow the rate of the parcel? It cools because the air is expanding. So hold on, where's my mouse? Where's my mouse? I can't find my mouse. Gosh. So what could you do? And the answer is you saturate the parcel. You saturate the parcel because if the parcel's saturated, what's forming? If the parcel is saturated, what forms in the parcel?
Cloud.
A cloud.
Clouds.
What is a cloud made out of?
Water vapor.
No. Survey says. By the way, do you know how long that show has been on TV? My entire career I could do survey says. Do you ever watch Family Feud? Do you still watch it today ever? Do you at least see some of the memes where they go, oh, check this one out, it's very funny? Yes or no? Family Feud, yes or no? Have you seen it? Okay. What's a cloud made out of?
Liquid water.
Liquid water. Okay, so I'm going to give you some real little bits of basics on this. I have a bunch of liquid water and I add heat to it. What happens to the water when I add heat to the water?
Starts to evaporate.
And when it evaporates, what does it become?
Water vapor.
And what do you know about water vapor? First fact.
It's invisible.
It's invisible. So I take liquid water, I see something visible, I add heat to it, and it turns invisible. It goes away, it becomes vapor. Now, you don't want to get this confused with steam. What's steam?
Steam is a cloud.
Yeah, but what's steam? What's it made out of? Google this. Do a Google search. What is steam? What does it say? Ryan, did you see what does it say that steam is?
It is the vapor into which water is converted when heated, forming a white mist of minute water droplets in the air.
Ooh, where'd you get that from?
Just from Google.
No, I mean, is there a site that it's from?
It's just what pops up on Google. It's
Oh,
not
okay.
from a site, yeah.
So a lot of people, some places, anybody see anything that says steam is vapor? That can't be right. Vapor's invisible, steam is visible. So really, when you boil water on a sink, on a stove with like a kettle or something, you're actually going from liquid to vapor. It recondenses into liquid droplets and then it evaporates again. On a cold day, you go outside, you breathe, you're taking vapor, turning it into liquid, and then it evaporates. So when you're boiling water on the stove, it's actually a 4-step process: liquid to vapor to liquid to vapor. And so if I said, draw a picture of a tea kettle with a cloud coming out of the spout, what's the one thing to be accurate you would need to draw? You'd have to draw space between the cloud, the steam, and the hole. There's a gap. In fact, if you had a contrail of an airplane, isn't there a gap between the airplane and where you see the condensation trail? There's always a gap there. It doesn't come right out of the engines. So we're going to talk about that as a type of fog that's called Arctic sea smoke or steam fog. That's what it's called. In any event, when you see steam, you just have to understand anything you see is liquid. There's droplets of water. So when water goes to liquid, when liquid water goes to vapor, what is that called? Evaporation. What is required? Heat. You have to give energy to the water to make it evaporate. That heat, there's a name for that heat. What is it called? It's called latent heat, L-A-T-E-N-T. Anybody who knows anything about psychology, what does the term latent mean? You know what the term latent means? Anyone? Bueller? What does it mean, Aaron?
Dormant.
Yeah, dormant. Like it's that would be a good word, like dormant or hidden. So we're talking about hidden heat, and that'll actually make sense as we go forward into this. but it takes heat. We call it latent heat. The definition for us of latent heat is the heat required or released from a change of state. That's our definition. Latent heat is the heat required or absorbed during a change of state. Okay? Now, if I said liquid plus heat equals vapor, what if I turned it around? When water vapor turns into liquid, what happens to the heat?
It loses the heat.
I'm sorry, Shannon, say that again.
I said it doesn't lose the heat.
It puts the heat back. So what
Yeah.
we're going to say is it's released. The heat is released to the air. So in a box, when I lift it and it saturates and I continue to lift the box, water vapor starts to condense. And what happens?
It gets cooler.
Latent heat is
Oh, yeah.
released. Where's it released to?
The air around it.
No. Because where is the vapor condensing? Where's the vapor condensing, Tom?
In the air?
No. Where's the heat? Where's the vapor condensing? You guys are doing pretty good. I know you,
Was it inside the box?
so Abhi, the answer, inside the box. The vapor is condensing inside the box. So where are you releasing the heat to? Inside the box. It is, what kind of a box is it?
Vegas box.
It's a Vegas box. So in other words, I'm not taking anything from outside in. Do you understand? Is that adiabatic if I'm heating the gas? Right? I mean, I said heat is released. I'm putting heat. What does the word adiabatic mean? What does the term adiabatic mean?
No, it wouldn't be adiabatic because it means cooling.
Oh, no. What does the term adiabatic mean, Julia?
No heat.
No heat. So am I heating air? Yeah. So is it adiabatic? No. But adiabatic means no heat's coming from where? Outside the box. Is this heat coming from outside the box? No, it's already in the box. Where was it? It was hidden. It was hidden in the water vapor. The water vapor had this hidden heat that it's now releasing to the air inside the box. So it's an adiabatic, not really, not by the term no heat, but it is sort of adiabatic because it's not coming from outside the box. So we say the word pseudo adiabatic, P-S-E-U-D-O, adiabatic. So the term pseudo adiabatic is being used because it's right. Pseudo, like a pseudonym, is Mark Twain is the pseudonym. It's the sort of name of Samuel Clemens. So pseudo means sorta, but sorta is not very scientific, so we go pseudo. So is it adiabatic? Sorta. It's sort of adiabatic, so we call it pseudo adiabatic. The book will call it wet adiabatic or moist adiabatic. Most people don't like the word moist. I'm not sure why, they just don't. But they use wet adiabatic, pseudo adiabatic, moist adiabatic. So Sam, in the other class, we have a pseudo adiabatic diagram. That's what they're called. Anyway, the heat is being released inside the box, but the water vapor is releasing heat. So that would make the box warmer, but it's happening as the box is getting cold. Listen, write this down. The water vapor condenses as the box is getting colder, present imperfect. Because heat is being given off then, what's the rate of cooling going to be? Here, I'm gonna break you guys. I'm gonna break you guys up into, let me see, 1, 2, 3, 4, 5, 6, 7, 8, 9, into 3 groups. And you need to answer that question. Heat is being released into the box. The box is releasing heat as the box is getting colder. So what happens to the rate of cooling? So I'm going to put you into breakout rooms and let you talk about it, because again, getting to level 3. There you go. Give you 2 minutes. Somewhere I need to break you of the habit of listening and thinking you know. You have to have the knowledge. So once again, I lift the box of air, it expands. Expansion is cooling. Cooling is happening because of the laws of thermodynamics that says expansion is work. Work requires energy. Energy comes from within. 1/2 mv squared is what's in the parcel, the kinetic energy of the molecules. But when water vapor condenses, there's hidden heat that is being released, which we will explain a little bit better later. That heat is slowing the rate of cooling of the parcel. Therefore, the parcel will cool at a slower rate and be much more likely to be unstable, because instability is a race between the environment and the parcel. Just understand this, that cloud forming is the parcel. It's what's happening in the parcel. The environment is what the environment is. It stays the same. Whatever it's doing outside today is what it's doing today. Tomorrow might be different, so we measure it all the time. We're measuring the atmosphere. But for the instability, we have to understand the environment is something you need to be given. The parcel is something that you calculate. How much slower is the rate of cooling?
I was just going to ask that.
How would you answer that, Tim?
It depends on how much latent heat is in there.
That's exactly the correct answer. The wet adiabatic lapse rate, gamma sub W, is less than the dry adiabatic lapse rate, depending on how, and there depends on how much latent heat is being released, how much water vapor is condensing. We need to make sense of that using terms that is going to mean something. And that's what that lecture that you're going to do online is about. It's defining some of the terms we need to actually answer that question. But Tim's answer is exactly right. It cools at a slower rate. How much cooler? Well, it depends on how much heat is released. Doesn't that make sense? The more heat, the slower the rate of cooling. Guess what? That rate of cooling changes depending on what the dew point is. The dew point affects that rate of change. And that's where we have to tie the ends together. That's what we'll talk about. So how are we doing up to this point? Where's your level of understanding now? Well, okay, so everybody seems to be doing a little bit better. Do you believe me yet on what it takes to learn something? That communicating it is the way that you get to level 3. And level 3 is learning. Level 2, memorizing a few facts and spewing them in the back. Because if I gave you a bunch of facts, do you agree that within a year you wouldn't remember any of them? You don't remember facts. You have to learn how to ride a bike. Then you got something. Okay. that's where we'll end off today. You have that other lecture. I would, if you want, go ahead and do that now. It's still class time, but I want to give you that chance. And then the test is also something that you can do. So you get to make a choice, but make a good choice. And do not come to class on Tuesday without knowing that lecture and taking really good notes at it, because I'm going to start out with the quiz based on the stuff that you have, okay? Any questions?
Is the chapter 6 notes also due on Sunday?
Yes. Although Julia, I think I said that if you turn it in on Monday, I'm not gonna count anything as late. Just do it before class.
Okay.
So things for next week, you have the test to take, you have a lecture to listen to, and I'm giving you the time right now to do that. So I'm giving you that hour back, and then you have a that worksheet to do. So it's homework, but you can prioritize your time. That's the problem with 2 hours a week or 2 days a week classes. Everybody good? All right, guys, enjoy the day. Get your work done. Take advantage of this. Next week's temperature is supposed to be in the 60s. No, I'm lying. I'm lying to you. I was just trying to make you excited about life. Temperatures in the 30s. Woohoo! Maybe 40. We could see 40 next week. Okay, enjoy your week. If you have any questions, send me an email. I'll respond to them as soon as I can, okay? Peace out.
Okay.